Hello, everybody. Hey, this is going to be our question of the day for 4-8. So question of the day for 4-8. Okay. So what we have, guys, what we have in 4-8 is we have a ball. And this ball is coming in at an angle of 20 degrees, and it's bouncing off and is exiting at a velocity of 20 degrees. And we are going to have a velocity of 22 meters per second, 22 meters per second, and we're going to have an exit of 22 meters per second. Okay, so now the first question is what type of collision? Which type of collision is this? And it is going to be, it's going to be elastic because it bounces. It's going to be elastic because it bounces, but it's going to be, because it's going to be perfectly elastic is because there is going to be a conservation of, there's going to be a conservation of kinetic energy. So notice that it was 22 here and it was 22 there. So we do not lose any energy from that. And we'll kind of get back to this type of collision when we talk about it at the end. Okay, so question B is going to say, what is the initial momentum of the ball? So the initial momentum of the ball is just going to be mass times velocity. And the mass of our ball is going to be 58 grams, 0.058 kilograms times 22 meters per second. And that is going to give us 1.276, since we have two significant digits, that's going to be 1.3 kilogram meters per second. Okay, so that is going to be our initial momentum. And says, what is the initial velocity of the ball in the x direction? In the x direction. So if we look at it up here, right? So we're going to have an initial velocity in the x, and we're going to have an initial velocity in the y. And our hypotenuse, because this is x and y, we're going to have a right angle. And our hypotenuse is 22, and our angle is 20. So for part C, our initial velocity in the x direction is going to be our final velocity times the sine of 20 degrees. The sine of 20 degrees, because the sine is opposite, which is going to give us 22 sine 20 degrees. 22 sine 20 degrees is going to be 7.5 meters per second. We're going to have our initial velocity in the y, which is going to be v final sine theta, which is going to be 22, not sine, sorry, cosine, because now we are adjacent. So 22 cosine 20 degrees is going to be 20.673. And we're going to round that up to 21 meters per second. All right, so now D is asking us, what is the final velocity of the ball in the x direction, and what is the final velocity of the ball in the y direction? Now, we can see that it is bouncing off. So we are going to essentially have this and this. So because our hypotenuse and our angle did not change, we're going to get 21 meters per second in the y, and we're going to get 7.5 meters per second in the x. This was 7.5, except This is going in the opposite direction. Since we said to the right was positive, we're going to get negative 7.5. So when we go back to D, what is the final velocity of the ball in the x direction? V final x is going to be negative 7.5 meters per second, and the final velocity of the y is going to be 21 meters per second. 21 meters per second. Okay, so E, what is the change in momentum? What is the change in momentum of the tennis ball? Okay, so momentum is going to be equal to mass times V final minus V initial. Now, we know that there was no change in the velocity in the y direction. So all we really have to figure out here is in the x direction. So we're going to have 0.058 kilograms, and this is going to be negative 7.5 minus a positive 7.5, which is going to give us a change in negative 0.87. Negative 0.87. Negative 0.87 kilogram meters per second. All right, so part F, calculate the impulse of the wall on the ball. Calculate the impulse of the wall on the ball. Okay, so impulse is equal to the mass times the change in velocity, or just the change in momentum. And therefore, we are going to have negative 0.87 kilogram meters per second. Now, we could change that and just call it Newton seconds. So typically, when we talk about impulse, we're talking about Newton seconds. And we talk about change in momentum, it's kilogram meters per second, but they're really just the same thing. Okay, G. If the ball is in contact with the wall for 0.25 seconds, what is the average force of the wall on the ball? Okay, so we're going to move it over here. We're going to go, sorry, did we forget something? F, calculate the impulse of the ball on the wall. So that was negative 0.87. G, calculate the average force. Okay, so G, impulse is equal to the average force times time. So impulse divided by time is equal to average force. And our impulse was negative 0.87 divided by 0.25 seconds. A Newton second, a second cancels out, and therefore we are going to get an average force of negative 3.5 newtons. That is going to be our average force. And finally, H. How much work is done? Now this, you guys, this is really perplexing because there is no work that is done. And if we kind of go back to here, okay, remember that work is equal to the change in kinetic energy. And we have the same kinetic energy. We have the same kinetic energy before and after. So you might be thinking that that is impossible. How can we have no work? We can, in one way, think about this wall when it is hit by the wall does not move. So there's no distance. Force times distance is equal to work. Now, in reality, there would be a little bit of a movement of the wall, even if it's tiny amount. And we'd also have some
deformation. We'd have some deformation of the ball. We could have some internal structure that got deformed. In all of these cases, it is not happening because we have a perfectly elastic collision. And really, in our reality, that does not take place. It does take place on the molecular level when, for example, atoms in air, like an oxygen and a nitrogen, when they hit and collide, that is going to be a perfectly elastic collision for reasons you can kind of go into later when you talk about thermodynamics, etc. Okay, but for this, there is no work. All right, and that is going to be it. That is going to be it for this help with question of the day for 4.8.